Good afternoon, class. We are looking at Module 3, which covers chapters 5 and 6. Here's chapter 6, exponential and logarithmic functions. Here's the practice test. So we want to find the formula for an exponential function that passes through the points given 0, 2000, 2, 20, and f of x is in the form of a, b to the power of x. So what do? We plug in the pairs into the function f of x equals a, b to the power of x. So when we replace the x with 0, we get a, b to the power of 0, and that is supposed to be 2000. When we plug in 2, it's ab squared, which is supposed to be 20. As you know, b to the power of 0 is 1. Therefore, a becomes 2000. And so in this formula, we replace the a with 2000. So a, b squared is 20. So that means 2000. B squared is 20. That's the meaning of it. We can divide by 2000. And the right side becomes 1 over 100. And B has two answers, plus, minus 1 over 10. And we keep only the positive value. So this does give us two answers. But the base has to be positive. That's why we get 1 over 10. And that's the final answer in the form of a, b to the power of x. Liz deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it is compounded monthly? So let's actually plug in the given $10,250. First of all, this is a of t equals p times 1 plus r over n to the power of nt. P is the principal, r is the rate, t is the time in years, n is the number of compounding per year. This is being compounded unlike simple interest I equals PRT. So replace the P with 10,250 or with 0.044% or 0.04, T with 10 in general. So for part A, when we say monthly, N is 12. So replace it with 12, and at this point you have to plug it into a calculator. You can do that. 0.04 divided by 12 added to 1 to the power of 120 times 10 to 50, and it gives you $15,281.03. By the way, normally with money we go with 2 decimals. Same situation, but this time it's going to get compounded weekly. So back to this formula, we are going to replace the n with 52 because there are 52 weeks in a year. And again, plug it into a calculator, and this will be a little bit more than that. What if we do this continuously? Then the formula becomes a of t equals p e to the power of RT. We plug in, t is 10, r is the same 0.044%, t is the same 10. We plug in with the initial value or the amount of deposit of 10,250. And we end up with a number which is a little bit larger than that, $15,291.20. What is the doubling time? Doubling time means whatever the initial value, in this case, whatever the principal, we end up with 2 times that. So if it's 10,250, it becomes 2 times that, which is $20,500. However, you really don't even have to know what this is to come up with the T. What matters is the R. So instead of this amount, we're going to write 2 times P because that's the meaning of doubling time, in which case we can drop the P from both sides. Now, I can take the natural log of both sides. So ln of the right side, ln of 2, is ln of the left side, ln2, and ln of the right side becomes simply R times T. Therefore, if you're solving for T, divide both sides by R. T is ln2 over R, and we know R to be 0.04. So that's all we need, 0.04, the R, the value of R, and it takes a little bit more than 17 years.
Could you re-explain D? I'm not sure how you got from 2P to PERT.
That's the formula that we have. A of T equals PERT. This is the continuous compounding, right? So A of T equals PE to the power of RT. Here's the formula for compounding continuously. And we use that for part C. Now, if it's going to be doubling, this A of T becomes 2 times the P. Do you see that? P is the principal. Doesn't matter if it's 10,250 or any other number. This P, when we discuss doubling time, becomes 2P. Does that make sense? So I'm using this formula. I'm going to replace the left side with 2P and the rest follows. Does that make sense?
Yes, thank you.
My pleasure. Use the graphs shown to answer the following questions. And all of them are in the form of AB to the power of X. Remember, it's an exponential function. And the exponential B is the base, and it must be positive. And if you recall, the ones on the right side, B is larger than 1. The ones that are decaying, B is between 0 and 1. So in general, we should know the ones on the right, the base is larger than 1. The ones on the left, the base is between 0 and 1. So that's from intermediate algebra. Now, which one has the largest value of B closest to y-axis on the right side? Because remember, on the right side, the B values, the bases, are larger than 1. On the left side are less than 1. They're between 0 and 1, like 0.1, like 1/2, things like that. So in this case, it makes it graph D. As you can see, among the ones on the right, this is closest to the y-axis. Which one has the smallest value for B? Now this time closest to the y-axis on the left, because on the left, the numbers are between 0 and 1, and all of them on the left have the base which is less than each and every one of them on the right. So it's on the left, and the one that is closest in this case is graph C. Which of them has the largest value of A? Which of them has the smallest value of A? We are looking at this, okay? If we let X be 0, then B to the power of 0 is 1. And therefore, we are looking at 0, comma A. which is the y-intercept. So which one has the largest y-intercept? This point, the largest y-intercept. If you look at the y-axis, the largest value would be here for those graphs. Therefore, it's graph C. Which one has the smallest? Again, we are looking at the same concept, namely the y-intercept. And look at the y-intercept for this one, for this one, for this one, for this one. I hope you see that this has the smallest y-intercept. Therefore, the answer would be part F. We want to use transformations of the graph of f of x equals 2 to the power of x of the function below. State the horizontal asymptotes, the domain. So let's see what happens, starting with the general concept y equals 2 to the power of x. Again, what I want you to notice is that when the base is larger than 1, it's an exponential growth looking like that. The domain is from negative to positive infinity. The range is 0 to infinity. 0 is not included. This is your horizontal asymptote, and this point is the y-intercept located at 0, 1. So let's write this. This is located at 0, 1. This is HA. The x-axis of y equals 0. It's an exponential growth. Domain is all real numbers, or 1, or you can say minus infinity to positive infinity. Range goes from 0 to infinity. Again, reminding you of things you've seen, you are supposed to know. So let's look at, so this point has coordinate 0, 1. Let's look at what happens here with 2 to the power of minus x. So x changes to minus x, which means you're going to reflect it with respect to the, so you're changing x to minus x with respect to the y-axis, looking like that. So your y-intercept stays the same. Your horizontal asymptote is not changing. Your domain is not changing. Your range is not changing. So what is changing, that this was the exponential growth, now this is the exponential decay. So y equals to the power of minus x. Horizontal asymptote remains the same, domain remains the same, range remains the same, but it's an increasing function or exponential growth. This is a decreasing function or exponential decay. Let's look at 2x plus 1, 2 to the power of x plus 1. So basically, we are looking at this graph, we are going to shift it up by 1 unit. When we do that, what happens is this. Now we have a different horizontal asymptote. So what does it mean? The domain has changed. Your y-intercept of 0, 1, now it has coordinates 0, 2. The domain is the same, but the range, instead of going from 0 to infinity, now it's going to go from 1 to infinity, and the horizontal asymptote of y equals 1. So this point has coordinates 0, 2. The function has gone up, so this has gone up by 1. The result is that the horizontal asymptote is no longer y equals 0, it's y equals 1. The domain hasn't changed, but the range from 0 to infinity has changed to 1 to infinity. Now we have the function f of x equals 4 to the power of x, and essentially looks very close to y equals to the power of x. When I write a function that results from shifting f of x 3 units up, so just go up, that means add 3 units. Now we want to take it to the left by 5 units. So x changes to x plus 5 because it's going to the left. We want to reflect f of x. We are going back to the original function about the x-axis. So because it's about the x-axis, you're really changing the y from y positive. Now it becomes negative. In essence, you put a negative in front of 4 to the power of x. Whereas in this case, when we want to reflect it about the y-axis, then you change the x to minus x. So those are the transformations. So we have the graph of f of x equals 2 to the power of x that has been shifted such that we have this one. So we started with this, we ended up with this. We want to write the equation for that. So let's do that. First and foremost,
I have a
f of x, or
question
yes,
about the one that we just did. When you're shifting units to the right, would it be negative? Hello?
when we go upward, plus 3. When we go units to the left, it's positive, to the right is negative. You're talking about this one?
Yes.
Okay, when we remember, along the x-axis, it works the opposite of along the y-axis. Along the y-axis, when you go upward, you add, and you go downward, you subtract. But when you go to the left, it's plus 5. When you go to the right, it's minus.
Okay,
That is the
thank you.
transformation. Sure. So we have f of x or y equals 2 to the power of x, the general basic function, and an exponential growth. We notice this is going up, in essence, this is going down. There seems to be a reflection across the x-axis, looking like that. So this one has the equation minus 2 to the power of x. So that's the blue one. This is the graph. Now this has shifted up. If you look at this one, this is similar to that, but now we have a horizontal asymptote of y equals 3. Take a look at this. Horizontal asymptote is the x-axis for both cases, which means y equals 0, by the way. It has shifted up by 3 units. So take a look at what happens. If we shift this up 3 units, 1, 2, 3. So that's what we are dealing with here. Look at this horizontal asymptote of y equals 3. The same thing here. So y equals 3. So we have this function plus 3. It has shifted up by 3. That's the green one, or the one that you have here. So a quick recap. Y or f of x equals 2 to the power of x, sort of the red color. The blue one flips over with respect to the x-axis minus 2 to the power of x. And the green one, we bring it up by 3. And that's what we have here. This is the graph. So f of x is minus 2 to the power of x plus 3. Those are the transformations. That's as far as the graph goes. There are quite a few properties of logs you should know. So before even we get to that, I want to just show you this. If you look at this, log x base b equals y, and the arrow that I'm going to put up, it means b to the power of y is x. In other words, if you can make the transition from here to here or vice versa, then you have no problem with any of the properties that are discussed here. And remember, the base must be positive, the base can't be 1. So here's the properties as an example. Log 1 with any base is 0. Take a look, b to the power of 0 is 1. That's the justification for that. Log b base b is 1 because b to the power of 1 is b. And what it says is that if the argument and the base are the same, log has a value equals to 1. In this case, these two together refer to this concept, meaning logarithmic functions and exponential functions are inverse of each other. You've seen this in intermediate algebra. I hope you remember that. This is the product rule. Log xy is log x plus log y, same base, b. Log of x over y is log x minus log y. All of them same base, b. This is the quotient rule. And this one is the power rule when the exponent becomes the coefficient. When the base is e, we call it natural log, and we use ln instead of log. When the base is 10, we just don't write the base and we use log. And obviously, this is the change of base formula. Okay, let's quickly see how we write this. Those are very elementary. We've seen them many times before in previous courses. For example, 5, just go with the arrow. 5 to the power of q is m. Whenever there is no base, but you see ln, the base is e to the power of z is v. Whenever there is no base, but you see log, the base is 10 to the power of t is w. So you should be able to make that transition. Now, we want to go back. Log base 3 of y is x. Log base e, so we write ln h because the base is e, ln h is k. Now, log b base 100 is a. So going from one format to the next. State the domain, vertical asymptote, and the end behavior of the function. So y equals log x. When we change x to x minus 7, it has shifted to the right. So notice, when we have minus 7, it means has shifted to the right by however many units here, which happen to be 7. So this one is a basic logarithmic function. This one has coordinates 1, 0. We move it to the right by 7 and it becomes 8, 0. Therefore, it has changed the domain. The domain was 0 to infinity. Now the domain is 7 to infinity, but the range, which was all real numbers, up and down, makes no difference. We still have the same range, but the domain has changed. It's important to see. Vertical asymptote, it was the y-axis, or x equals 0, and now it has shifted to the right by 7 units, x equals 7. Simply put this one equal to 0, this expression, if you set equal to 0, x equals 7 is your VA, short for vertical asymptote. So domain has changed to 7 comma infinity, and the range is the same. The end behavior, as x goes to infinity, y goes to infinity for both cases. But in this case, as x goes to 0 from the right, we should say, f of x goes to negative infinity. In this case, as x approaches 7, f of x goes to negative infinity. I hope you see the concept. So if we want to be more precise here, this is the notation you'll see in calculus. You really have to say as x approaches 7 from the right, this plus sign you put, that means 7 from the right. You'll see that in calculus courses. But again, if you look at the basic law, again, or this one, both of them go to infinity as x goes to infinity. But in this case, as x goes towards 0, then it goes to negative infinity. In other words, towards its vertical asymptote. This one, the vertical asymptote is 7. And again, from the right side, because it is not defined on the left side of the vertical asymptote. State the domain, vertical asymptote, and the end behavior of the function. And again, as I mentioned, basically you set this equal to 0 and it gives you the vertical asymptote. But let's discuss everything, how it looks like, and everything starts with ln x, which is a basic function, a logarithmic function. And when we change the x to minus x, that means we are going to reflect it. We are changing the x to minus x, reflected with respect to the y-axis. So take a look at what happens here. So this is y equals ln x. Maybe I write next to it. So this is y equals ln x. And this is y equals ln of minus x. So this one has coordinates 1, 0. This one has coordinates negative 1, 0. So we have changed the x-intercept from 1, 0 to negative 1, 0 when we flipped it over. Now, we are going to replace the x with x minus 2. That negative sign is not changing. We are changing the x to x minus 2. Therefore, because of negative 2 along the x-axis, shifts to the right by 2 units. Shifts to the right by 2 units. Therefore, this negative 1, 0 moves to the right by 2 units. If you add a 2 to the x, negative 1 becomes 1, 0. So it goes back to 1, 0. I hope everybody can see why, because minus 1 plus 2 gives you this new point. So this is the graph of g of x equals ln 2 minus x with the vertical asymptote. Set this one equal to 0. Vertical asymptote x equals 2. So this, again, as I said, it has also looking like this if I wanted to write it next to it. So I would write here and the vertical asymptote as coordinate, has the equation VA x equals 2. So let's discuss the domain and range. As you can see, the range hasn't changed in all cases from negative to positive infinity, up and down. But what about the domain? The domain from negative infinity all the way to the vertical asymptote, which is 2. So from negative infinity to 2. So the domain has changed. The range has. What is the end behavior? As you can see, as x goes to negative infinity, as we go this way, y goes to positive infinity. But over here, when we come to x equals 2, as x approaches 2, this time from the left, y goes down to negative infinity. So we write when x approaches 2, when we get closer and closer to 2 from the left, g of x, since it's called g of x, the function goes to the y coordinate, if you will, goes to negative infinity, whereas when x goes to negative, and when we move that way, this is moving up. So the y coordinate goes to infinity. It's important to distinguish between x and y, where g of x or f of x or h of x, they represent the y coordinate in essence. All right, we want to discuss this function, and again, we want to go over everything: domain, asymptote, behavior of the function in the long run, or the end behavior. So we start with log x. Y equals log x, and we look for log of 3x. So what happens is this. First class, the blue one is log x. The red one, it's a horizontal shrink by a factor of 3. Okay, so this one has coordinates 1, 0. So the red one is the basic y equals log x. Let me write it. And we should know the domain from 0 to infinity ranges are real numbers, so on and so on. It has a vertical asymptote, which is the x-axis, or y equals 0. Now, when we multiply the x by 3 along the x-axis, it shrinks by a factor of 3. And so now the new point, as far as the x-intercept is concerned, is 1/3. So notice, if you replace the x with 1/3, you get log 1. And by the way, log 1 is 0. So that's what happens. So this one is the blue one. So the blue one has the equation y equals log 3x. All right. The next one is to get to -4. And remember, we've taken, in essence, number 3 out. So in order to get to -4, so we can say 3 times x minus 4/3. Please understand, if you distribute the 3, let me do that so everybody can see what's happening there. If I distribute the 3, I get 3x minus 4, which is the same as this one. We want to get this parenthesis, 3x minus 4. So what this means, it has shifted by 4/3 of a unit. So this point, we are looking at the blue one, this shifts to the right by 4/3. And so now this blue point has got to the green point, which has the coordinates 5/3 0. So I want to quickly recap. Original function 1, 0. It changes to 1/3 0. And now because we've shifted to the right by 4/3, 4/3 and 1/3, they add up to 5/3. So this point has coordinates 5/3, comma 0. So we got this one. Please understand that's the same thing. Now we're going to do this negation. We're going to flip this over. So when we put the negative in the front of the whole function log, then it flips over with respect to the x-axis. So the green function will flip over and looks like this function. So the effect is as it flips over, the location of the x-intercept, which was 5/3, comma 0, that doesn't change, it just flips over. Now, +3, that means now pick it up, okay, and take it up by however many units in this case, which is 3 units. So we're going to take it up by 3 units. So this still has the 0.5/3, comma 0 as the x-intercept. Now with the +3, we are going to shift it up 3 units. And so now this function has gone up. This function has gone up by 3 units. And so what we notice is this point, which had coordinates 5/3, 0, has gone up to 5/3, comma 3. So this point, 5/3, remained here, comma 0. Now it's gone up to 5/3, comma 3. And what is the vertical asymptote? Basically set 3x minus 4 equal to 0. 3x. And it gives you the vertical asymptote. So we are going to look at the graph and write the information they're asking us. The domain is from 4/3 to infinity. The range is not changing. It's still all real numbers, negative to positive infinity. As x goes to infinity, as x goes this way to infinity, seems to be going down to negative infinity. As x becomes closer and closer to the vertical asymptote of 4/3, it goes to positive infinity. Therefore, we write domain from 4/3 to infinity. Range doesn't change, minus infinity to positive infinity. And behavior. As x gets closer and closer to 4/3, it blows up to infinity. As x goes towards infinity, this is going down to negative infinity. All right, we have all of these properties we should be comfortable with. We want to expand each log. We want to decompose it. We use the product rule. So this is log of x plus log of y plus log of z. And always use the same base. In this case, it's 7. This one uses the quotient rule, ln 9 minus ln of x. This uses the power rule. Take a look. N becomes the coefficient, so 10 becomes the coefficient here. This one is a combination, so it's log of the top minus log of the bottom. We can do it in a couple of steps. So this is log of the top, a squared b to the power of 4 minus log of the bottom, which is C7. And as always, use the same base. Whatever the base is, don't forget. Now, this part, I can change it to log of a squared, whatever the base, plus log of b to the power of 4, the same base. And in all cases, The exponent becomes a coefficient. 2 sits in front, 4 sits in front, 7 sits in front, and here's the final answer. 2 log a base x plus 4 log bx base x minus 7 log c base x. It's important to be careful with the base, everybody. We want to continue with decomposition. So we're going to write this a parenthesis to the power of 1/2 because it's a square root. If it were cube root, we would say to the power of 1/3. And so 1/2 sits in front. So we write 1/2 log x cubed y to the power of 5. So 1/2 log x cubed plus log y to the power of 5. I can put the 3 in front, 5 in the front, and with 1/2, when we multiply the first one, 3 in front with 1/2 is 3 halves. The second one, 5 in front times 1/2 is 5 halves. And there you have. We're looking at the quotient rule. ln of the top minus ln of the bottom, and there is nothing else we can do. Let's do the same thing, log of the top minus log of the bottom first. Let's make some changes. So this is log base 4 of x to the power of 5 plus log base 4 of 10y to the power of 1/3. And the last one, we are not changing. Same thing, minus this. So what happens is, this one, 1/2 sits in front, 1/2 log x base 4. This one is 1/3 log base 4 of 10y. I want to show you that what happens to this one, minus 10 log base 4 of z. This one, here's a different color. This one is 1/3 log of 10y. And all of them have the same base, remember that, base 4. And this one is 1/3 log base 4 of 10 log base 4 of 4. And that's what we get. So let's quickly recap the whole thing. This one, 1/2 sits in front. This one, 1/3 sits in front, and we expand the 10y to log 10 and log 1. And this one, 10 sits in front. This is a complete decomposition of log. Complete decomposition of log. Let's go back and combine it. Let's combine these two. When we multiply the two, we get 6x to the power of 9. Part B, we're going to divide, and we get this one. In part B, everyone, we are using the quotient. Remember, you can go from left to right, you can go from right to left. So we are going from right to left. How about this one? I'm going to get rid of the 2 and put it here. I'm going to get rid of the 3 and put it here. I'm going to use the product rule, and this is what I get. Now, in some cases, in some text, they may expect you to multiply, not me. Okay. All right. Let's go to part D. First and foremost, I get rid of the 1/2. I get rid of the 3. So what we have here is log x minus log y to the power of 1/2 square root of y plus log c cubed. And I hope you can see that these two can be combined because they both have a positive sign, so you can combine it into log x c cubed minus log of square root of y. Of course, you can do it in one shot. Anytime you have a negative sign, that means a quotient rule, and that's the final answer. Do you have to take that many steps? No, you can do it in one shot. It's absolutely up to you. All right, we want to solve these equations. We know we can combine these two if possible. In this case, it doesn't happen. When it happens, I will show you. Because they have the same base, namely 5, they must be the same. They're exponents. So minus 4x minus 3 must be equal to minus x. And let's move things around. So if I move this to the right, at 3x equals minus 3. If I divide by 3, I get negative 1. We can change this to 4 cubed. Now we can combine these two. So this becomes 4 to the power of 3 plus 3x. So if they have the same base, namely 4, they must have the same exponent. That means 3 plus 3x must be equal to 2. I can subtract 3. That gives me negative 1, and I'm going to divide by 3, and that's my final answer.
Why didn't you make 4 to the power of 3x 1 to the power of 3x? Because you divided 64 and 16 by 4?
That's not what I did.
Oh, could
That's
you
not
remind me
what
what you did, please?
I'm changing 64 to 4 cubed.
Oh, okay.
And since they both have the same base, I'm going to add, on the left side, I'm going to add the exponents. I get 4 to the power of 3 plus 3x. I'm not dividing by 4. I can't do that. And so the left side becomes 4 to the power of 3 plus 3x. The right side is 4 squared. Since they both have the same base, namely 4, they must have the same exponent. So 3 plus 3x must be equal to 2. Does that work?
Yes, thank you.
My pleasure. And then I'm going to get rid of the 3. I'm going to subtract 3, and 2 with negative 3, they give me negative 1. Remember, this is gone when I move that. So I have 3x equals negative 1, and x becomes negative 1.
Oh, why did we add 3 plus 3x instead of multiply?
This is called the product rule. A to the power of m times a to the power of n is a to the power of n plus m. This is called the product rule of exponentials.
Okay.
So a to the power of m over a to the power of n is a to the power of m minus n. A to the power of m to the power of n, which is the power rule, is a to the power of m times n. So these are simply put exponential rules. Okay.
That makes
Now,
sense. Thank you.
my pleasure. We want to solve this, so we are going to divide by 2 first. The next step is to undo the exponent. To undo the exponent, you have to take a log of both sides. To take a log of both sides, when you look at this, you notice the base is e. To undo that, you take a natural log. Therefore, ln of the left side equals ln of the right side, and ln of the left side becomes 3x. So I hope you see, again, this is one of those exponential rules. Ln of e to the power of 3x is 3x. So what is x? Divide the right side by 3, or you can say multiply it by 1/3. It means the same thing. Now, this is the exact answer, everyone. Again, I'm simply dividing this by 3 or multiplying it by 1/3, the same thing here. This is the exact answer. If you use a calculator, it gives you a rough estimate, as you can see. We want to solve this. We can factor this such that we want 2 numbers, the product is -6, the sum is -1. And this is about factoring. Or if you can't see what we have done here, you can let e to the power of x, let's say, be y, which means e to the power of 2x is y squared. And so now this one becomes y squared minus y minus 6 equal to 0. And you factor this one into y minus 3, y plus 2. In any event, it's just a matter of fact. So the first one says e to the power of x is 3. The second one says it's -2. So if I want to get to x, what do? I take a natural log of this. So x becomes ln 3, but this one has no solution. I want to make sure everybody understands what's going on here. Take a natural log of this, and it becomes x. This becomes ln 3. Exact answer, rough estimate if you use a calculator. What about this one? Remember, exponential functions have a range from 0 to infinity. E to the power of x can never, ever be negative. It can't even be 0. So this has no solutions. This has no solutions, class. Only the first one that gives us the answer. All right, we want to solve this. We are going to go with the arrow, just to remind you, this is the arrow, right? 3 squared is 9k, or 9k is 3 squared. And we know 3 squared is 9, so we divide by 9. And k becomes 1. To solve this, we're going to combine 2 combine these two into a single log. That's how you solve when you have a logarithmic equation where one side is log, one side is a number. So log of 4 times minus 5x, meaning log of negative 20x must be 2. And now the arrow, we go with the definition. LOG has no base, the base must be 10. So 10 squared is minus 20x. As you know, 10 squared is 100. So we're going to divide both sides by negative 20. And x becomes negative 5. They have the same base, 7 and 7. They must have the same argument. So 5n minus 2 must be equal to 8 minus 5n. And all you have to do, move things around, meaning let's move this here to the left, this one to the right. 10n is 10, and n becomes 1. When you have all logs and nothing else, you don't have to move things around. Just make them into a single log. The right side becomes log of 12x. So the left side doesn't change because it's a single log. They have the same base, namely 10, because the base is missing. LOGs, the base is 10. So they must have the same argument, meaning x plus 12 must be equal to 12x. And I can change this to 11x, right? Subtract the x. If I divide by 11, I have the answer, and I'm done. Same thing here. We have all logs. So put them into a single log. This is fine. This one, change it to ln of x plus 4 over x. So the left side, we can combine it. They both have the same base, namely e. Therefore, they must have the same argument, namely x plus 4 over x is x plus 1. Now we do the cross product. One times x plus 4 is x plus 4. And multiply these two, I get x squared plus x. As you can see, I can drop the x. X squared becomes 4. And we have two answers, 2 or negative 2. However, we have to check. When you check the negative 2, it's fine here, but it's not fine here. ln of negative 2 is undefined, so this is out. As long as any of those expression becomes undefined, that one is out. So that's an extraneous solution that we came up with, doesn't work with the original equation. What happens when we have logs on one side and a number on the other? And if you happen to have them on both sides, bring all the logs to one side, all the numbers to the other, combine the logs. In this case, is log base 2 of x times x minus 1. And therefore, x times x minus 1 is 2 to the power of 1. Now we go with the definition. I'm assuming nobody has any problem with the definition. So x times x minus 1 is 2 to the power of 1. As you see, this is x squared minus x. This is 2. Move it to the left. Do the factoring. You want two numbers. The product is negative 2. The sum is negative 1. So x minus 2x plus 1. X is either 2 or negative 1. You should always check both of them, but 2, it gives you log of 2 and log of 1, and that works out. But what about negative 1 right away? The first one, what is log of negative 1? Undefined. That's out. That doesn't work. So get rid of this one. Be very careful. You must check your work. All right, we want to solve this. We are going to move the 10 and subtract it from 3. We get negative 7. 4 to the power of x is a negative number. It doesn't matter, negative 7 or any other number. It can't be even 0. So there is no solution. Exponential form, remember the range is from 0 to infinity. Can't be. 7 to the power of x minus 10 equals 1. Well, we can, since the base is 7 here, we can write this as 7 to the power of 0. Again, we choose 7 because the base is 7. Remember, I can write 8 to the power of 0. I can write 10 to the power of 0. Why am I writing 7 to the power of 0? Because the left side has base 0, has base 7. So they have the same base. They must have the same exponent. X minus 10 must be 0. And therefore, x must be 10. Very straightforward. Now, can we come up with the same base? No. When that happens, it's a little bit more complicated, but the process is very straightforward. So let's go through that. You can take a log of both sides in order to get to the variable. And to take a log, you have two choices. You can take a natural log, you can take a common log based in. Because none of them is e and none of them is 10, it doesn't matter which one. So let's take a natural log of both sides. This x sits in front, this x minus 2 sits in front. This is logarithmic property, right? Known as a power rule. So this is x ln 4, this is x minus 2 times ln 9. It is important to know ln 4 and ln 9 are numbers. But if you put them into a calculator, it's a nasty number with tons of decimals. So we're going to keep them the way it is, and at the end you can change it. So first, let's come up with the exact answer by keeping them the same. So I can distribute this. I get x times ln 9 and minus 2 ln 9. Since I'm solving for x, I'm going to bring all the x's together. So I'm going to move this way. I'm going to factor out the x. I get x times ln 4 minus ln 9. And now I'm going to divide both sides by ln 4 minus ln 9. And I get this one. Couple of things I want to mention. You see this negative sign is here, but I hope you see that I can take the negative sign down and get ln 9 minus ln 4. I hope you see they are identical. Okay, again, take a look. Whether I have it in this format or in this format, it's the same. The difference is this doesn't have as many negative signs. Now, what is this? This is an exact answer, everybody. They ask for an approximation, use a calculator and approximate it. But this is an exact answer. Assuming log 2 is A, log 3 is B, log 5 is C, all of them have some base. We don't know what the base is, we call them base B. Then we want to find log of 50, we want to find log of the fifth root of 300, same base B. To solve a problem like that, you want to cut the number and factor it into pieces involving 2, 3, and 5. So I hope you know that 50 is 2 times 25 or 2 times 5 squared, or you can factor it. If I were to factor 50 divided by 2 is 25. Remember prime factoring. I'm assuming you know that. 5, 5, 5, 1. Prime factoring. That's all I'm doing. Basic math. So this is log 2 plus log of 5 squared. So this is log 2 plus 2 log 5, same base, same base. I cut it in two pieces. So let me maybe write the intermediate step. So this is log 2 plus log 5 squared base B. And now you replace it and you're done. A plus 2C. Now, This one, we write it as 300 to the power of 1/5, and 1/5 sits in front. You have to cut the 300 into pieces. Now, in case, I mean, you may know that 10 is 2 times 5. We have 2 of them. So it's really 2 squared times 5 squared, and then we have the 3. But if you want to go with the prime factoring, divided by 2, you get 150. By 2, you get 75. By 3, you get 25. Divide by 5, you get 5. Divide by 5, you get 1. And that's when you're done. So this is what you have. And therefore, you cut this into log of 2 squared plus log of 3 plus log of 5 squared base b, and then 2 sits in front. So 2 squared becomes 2 log 2, 3 is log 3, 5 squared is 2 log 5, all of them the same base, keep the same base. Now plug in, this is A, so 2A, this is B, B, this is 2C. And that's the final answer.